Welcome to Tipsy Topics with Tory and Tom. We're excited to bring a new and cosmic collision program your way that's going to be a little atypical, but way more fun because we're going to get beyond what we're normally accustomed to presenting. However, before we introduce the speaker, I'd like to give some announcements about some upcoming exciting things at the Evansville Museum. So from now until August 22nd, you can enjoy our expert tattooing in the main gallery, and it's an exhibition that focuses on Midwestern tattooers. And every Saturday until August 21st, there is a free collector's tour with the purchase of a general admission ticket with Clint and Heather. They were the the lenders for the collection, and they will be there every Saturday from 1 to 2 to do a tour. And on August 8th, our joint exhibition, Escapism, does close, and we hope that you have an opportunity to come and see that exhibition. And then following that will be The Bridges of Paris. However, I'm going to wait for you to see some more information on our website. But if you love Paris, this is an opportunity to see some beautiful photography from an artist who photographed every bridge at night in black and white photography. We also have a classical and medieval numismatology exhibition open until October 10th, and that was a joint exhibition with USI and the University of Evansville. And for history, on Sunday, August 8th, 2021, at 2 p.m., talk by longtime and now retired journalist Roberta Hyman, Votes for Women, and Then What? Presented in conjunction with the current Evansville Museum exhibition, Votes for Women, Justice Delayed, that continues through Sunday, January 9th, 2022. Hyman's talk will share the untold story of Evansville's women's suffrage movement, the women and men who led it, and their enduring impact on our community. As seating is limited, please call the Evansville Museum at 812-425-2406 for a complimentary reservation. And with all of that aside, Tom, will you introduce our guest today?
Oh, I sure will. Gosh, we've got a lot going on. We must be a really fun place down on the riverfront. Go Evansville Museum. And we appreciate our visitors and invite everybody down to our wonderful offerings down here on the beautiful Ohio River in downtown Evansville. And gosh, yeah, we are going in a different direction. We're going into a science area, which that is certainly not my wheelhouse. So we're glad that it is in our special guest wheelhouse. And our special guest that it is a pleasure to introduce is Carlisle Wishard. And she's going to share with us, as Tory indicated, about cosmic collisions. And that's why you see me on the planet Mars today. I understand that's the place to be for cosmic collisions. So why not be where it's happening? And Carlisle is a fifth-year PhD student in the Earth, Atmospheric, and Planetary Sciences Department at Purdue University, our friends up north. Via her home in Virginia, and undergraduate studies at the University of Alabama. And happily, we got to know Carlisle this past spring and summer when she was an intern in our science department and working in our wonderful Cook Immersive Theater and Planetarium with our esteemed friend and colleague, Mitch Luman. It was great getting to know Carlisle just this past few months. Carlisle studies the early solar system, particularly early impactor populations and the craters they may have left on Mars's surface. She uses computer modeling to understand the dynamics involved in the formation and evolution of the terrestrial planets and to track potential impactor populations during this very early stage of our solar system's history. Impact craters are the most abundant and widespread geological feature in our solar system, and they offer crucial insight into our ancient past. And in this Tipsy Topics presentation, we're so excited that Carlisle is going to discuss the impact of craters and the aftermath of cosmic collisions. So Carlisle, it's our great pleasure to have you with us today and to turn it over to you for this most interesting topic.
Well, hi guys. Thank you so much for having me back. We are going to be talking, like you said, about cosmic collisions. I particularly want to talk about, like you mentioned, impact craters, which are kind of the scars left behind on planetary surfaces from these types of cosmic collisions. And I want to talk about collisions here on Earth, impact craters here on Earth. We're going to talk a little bit about the moon and then a little bit about Mars as well. So at the end of this talk, I'm also going to kind of talk a little bit about my work and where it's kind of going, how I like to think about the work that I do and try to explain how important these impact craters actually are to our understanding of the history of our solar system. So before we get into that, I want to talk just slightly, a little bit, very briefly about myself, just to kind of give a little bit more of a background on who I am and some of the cool things that I've gotten to do during my PhD here at Purdue. So like Tom said, I'm a fifth-year PhD student at Purdue. And some of the really awesome things that I've gotten to do obviously have involved space and science research in general. But on the bottom left here is like my most favorite picture I've ever taken in my life. That's a photo of me celebrating the Apollo 11 50th anniversary. And you can't really tell, but in my hands, I'm holding rocks from the moon. So these are samples brought back from the moon. It's so cool. It's like the coolest thing I've ever gotten to do in my life. On next to that picture is a photo of me on the rim of Meteor Crater. And I include that because we're going to be talking about Meteor Crater towards the end of this talk. And I want to highlight that it's a really cool place to go and visit if you happen to be in the area. It's like a tourist destination. So I highly recommend people going there if they're interested in craters. And then the top photo I've included, I think you guys will recognize the place that I'm sitting. That is from my internship at the Evansville Museum. That is me behind the console in the planetarium. So
Yay.
yes,
yay. Can I ask just briefly, how did you get interested in such studies in the beginning as a youngster?
Yeah, so I was really, really lucky in that my high school had a planetarium. I know they're becoming more common. I've heard of a lot more high schools nowadays kind of being built with planetariums. So I was really lucky to have one in my building. And my director there, she was wonderful. Her name was Leanne Hennig. I think she's still involved with planetarium work. She encouraged me to pursue planetary science, and that's what I went into undergrad kind of planning on, and then here I am in grad school. So it's really...
Okay, so it was not an abduction experience or anything like that.
No, well, if it was, I wouldn't tell you. So
yeah, that makes sense.
So that's a little bit about me, just to kind of give you a little bit of background of where I'm coming from. But I'm not the cool thing. The cool thing is the science. So this is a science talk, obviously. This is a talk titled Cosmic Collisions. But like I mentioned, we are mostly going to be focused on the aftermath of these types of collisions. And these aftermath of these collisions are impact craters. So like Tom said, impact craters are the most abundant and widespread geologic feature in our solar system. And that means that it is so important that we understand how they form, why they form, where they form. That way we can really kind of get an understanding of our solar system's past, our solar system's history, and our solar system's future. So we know that impact craters form when a meteor, you can think like an asteroid or like a piece of space junk, basically, comes down and strikes a planetary surface. Seems pretty simple. We can see here in this image that I've included, this is a map of all of the confirmed sites of impact craters here on Earth. So as you can see, they come in a wide variety of sizes. The colors indicate age, so they come in a wide variety of ages as well. And we're going to talk about, why that is, why they're all different sizes, why they're all different ages. And we're going to look at a couple of examples of terrestrial or Earth craters over the next few slides. So before we get into that though, it's important to understand what impact craters can actually tell us about the surfaces on which they form. So because now that we know how impact craters form, meteor coming down, striking a surface, because that is a random process, it's just random space debris coming down and striking our planet, meteors and impactors don't get to choose which planets and what place on the planets they actually form on. They just hit randomly. They impact all different planetary surfaces pretty much equally. So when we see surfaces like the two that we're looking at in this picture here, these are both surfaces of Mars. When we see these here, we can actually learn a lot about the ages of the surfaces just by looking at them. So when scientists are presented with a new planetary surface, be it like, we all just saw the surface of Pluto for the first time back in 2015. We had never seen the surface of Pluto before. First thing scientists did when they got those images back was do something called crater counting. And this is literally the process of looking at a surface and counting the craters on top of it. And I actually want, if we can, us to go through that little exercise right here in crater counting to just kind of explain what it is and how important it is. So if you look at the surface on the left here, this is Amazonas planitia on Mars. And you can see that this surface is pretty flat, pretty barren. There's not a lot of craters on it. I count maybe like 6 craters on the entire surface. And when you compare it to the surface on the right, this is also on Mars, the same scale. This is Arabia Terra. You can see that it's really, really heavily cratered, right? There are a lot of big craters, a lot of craters overlapping, a lot of eroded craters. Based on what we know, the surface on the right, Arabia Terra, because these are the same scale and we know how craters form, just random processes, all that we've changed is the size, number of craters on the surface. If we think about planetary surfaces as acting as like a kind of like a witness plate, the longer a surface is exposed, the more craters it's going to accumulate, right? So if a surface has been exposed longer, it's going to have more craters on the surface. So I want you guys, if you're looking at these two surfaces, which one do you think is older?
I'm going to say the right one.
Yeah, Arabia Terra, right? You're exactly right. Yes.
So it's sort of like people's faces, like your guys is compared to my number of wrinkles compared to smooth faces. Yeah.
I know,
Exactly.
Tom. I got them doctors helping me, so thank you, science.
So looking at these surfaces, we can't get an exact age, but we can get kind of a relative age. And so we know relatively Arabia Terra is older, and it's thought that it's about 4 billion years old, while as Amazonas planitia on the left is less than 500 million years old. So there's a really big age difference between these two surfaces. And we've gone through this exercise. You may be thinking, well, that was easy. This was really simple. Why does it take her 4 years to do this?
Come on.
Well, we were going to ask that.
I mean, but you're right? Like on the surface, it's easy.
No
But
fun.
the thing is, this is an incredibly powerful way of helping us map out the ages of different regions on planets. And this is really important because we've never been to Mars. I mean, we've sent rovers and stuff, but humans have never been there. We haven't brought anything back. We can't date the surface in any other way. So this is a really important way for us to date planetary surfaces and get the evolution of an entire planet without actually going there.
So, this again, out of my wheelhouse.
This
is one surface. So I guess my question is, how can you have different ages, especially that different, and that's a huge gap between Arabia.
Yeah.
And how does that happen? I guess is my question. Like, how does this happen?
Yeah, that's a great question. So these surfaces are not next to each other on Mars. They're in different parts of Mars. So kind of think about it like if you were comparing the age of like a beach.
Okay.
The sand is continuously covered over, reworked, that sort of thing, versus like a mountain. That mountain has been in existence for millions of years. It's there.
Mm-hmm.
So these are two different surfaces that have had two different histories. We don't know exactly where each one formed or when each one formed or how they formed, but we know that they had different histories. So
Okay.
does that kind of clear it up a little bit?
Yeah.
Yeah. So that's kind of what we do, right? And we don't know how these surfaces formed on Mars. We have some ideas, but the way that we understand their relationship to one another is through these craters and their age relationships. So, okay, so now that we know a little bit about how impact craters can indicate the age of kind of a surface that we're looking at, I want to take a look at the craters themselves. So there are two main types of impact craters that we're looking at here. And there are other subtypes that we're going to look at in the next slide. But for the main types of craters, there are these two. There are simple craters, which are simple, and complex craters, which are complicated. It's pretty easy. Simple craters are kind of what you might expect. They are basically just a bowl-shaped depression in the ground. I like to think of these like if you had a little pebble and you dropped it in like dirt or sand or something, it would just form a little depression. It would be exactly what you would expect. On the right, you have the complex craters, and those are not a simple bowl shape. These have that nice defined rim around the outside. They have that central uplift. And these are a little bit harder to wrap your head around. But the way I like to think of it is if instead of dropping your little pebble into like sand or dirt, you drop your little pebble into like a lake or a pond. If you think about what happens there, you have those ripples outward, right? And then you have that central clip upward of the water from where you dropped your pebble. That's exactly what's happening here. So much energy was imparted into the ground that it kind of behaved like a liquid a little bit at the time that this was formed. And you can see those ripples coming out of it and that central uplift kind of frozen in time. And so that's what we're kind of looking at here, these two different types of craters. Now, there are other types of craters, and we were going to talk about those. They're subclassifications of different types of craters. And the important thing to know is that the type of crater that forms from an impact event depends on the size of the meteor or impactor that creates the crater. So the bigger the asteroid, the bigger the impactor, the more intricate, the larger the crater that forms is going to be. So on this diagram here, we see 5 different types of craters. The only one I don't work with in my research is the smallest. This is a pit crater. If you can see the scale at the bottom, these are like 10 micrometers in scale. So they're like, you'd have to look under a microscope to see them. So I don't deal with anything in a microscope. I just deal with stuff that you can see on a planetary surface. So my work starts with the simple craters, which are like a kilometer across, up to 10 kilometers across, kind of, into the complex craters, which are those that have the rim and the upward plip. These are like 10 kilometers across or so. Larger craters than that can form something called a peak ring basin. So this happens when it's so big that that central uplift actually spreads out into a ripple itself. So it spreads into concentric rings. And more concentric rings you get into a multi-ring basin. And these are massive. These are like upwards hundreds, thousands of kilometers across. And these are pretty rare. We see a couple in the solar system, but it's not like you have to be worried about like existential threat of one of these coming down and killing us all. Probably not going to happen in our lifetimes.
So for us folks here in America, can you remind us a kilometer to a mile is about?
Oh, yes. Oh gosh, I don't even know how a kilometer to a mile. It's like half, right? Or a third about. Something between 2 and 3 kilometers make up a mile. I can Google it.
Well, I thought you were going to mention about the...
I see 1 kilometer is equivalent to 0.6214 miles. So
Okay.
0.6 miles approximately to a kilometer. I Googled it. I do not know this.
Good. I'm glad you Googled it because I would have had to Google it too. See, in science, we all deal with the metric system and it just doesn't connect in my brain.
Yeah, well, when you look at it logically, that's where we should be, but I don't think we perhaps ever will be.
I hope so. It would make my life a lot simpler.
Yeah.
So, we have these different scales and some of them are obviously massive, obviously, planet altering events. And we've talked about some of these, and I want to talk about now what we would see on Earth. So some of the cool craters that we can see here on Earth. And the first impact event that I want to talk about is the most famous impact event in all of geologic history. And this is, of course, the asteroid that killed the dinosaurs. So I want to talk about this a little bit because it's really cool and everybody loves this impact event. I don't know if love is the right word because it killed everybody's favorite animal, the dinosaurs, but this impact event is known as the Chicxulub Impact Event because the center of the crater is near the present-day town of Chicxulub, which is a town in the Yucatan Peninsula in Mexico. Obviously, that town didn't exist at the time that this crater was formed, but that's how we name craters for the most part. And while we've known about this crater since about the late 70s or so, it actually wasn't confirmed to be the dinosaur killer until 2016.
Wow.
So this is all, really new, pretty recent sort of information that we're getting. We know that this crater formed about 66 million years ago, so pretty recently in geologic time, and it formed from about a 10-kilometer asteroid. So kilometers again, that's a couple miles across. That's a pretty big space rock coming down and hitting us. Yeah. This crater is about 150 kilometers across, and which is about, I did do this calculation, this is about 31 miles across. Because
that's crazy.
Yeah. So if you think one end of that crater is in Evansville, right? The other end is in like Owensboro, Kentucky. That is a massive, massive crater. In fact, this crater is so big, it is the complex crater type that we talked about, the peak ring, where it's got that central uplift that then spreads into a ring. And we can actually see that if we look at this image here. So this image is a map of the gravity signatures of the basin. And basically what that's telling you is what the basin would look like if it wasn't buried beneath millions of years of sediment. You can really see that central ring. Let me see. Can you see my pointer if I pull it on here?
Oh, yeah.
Do you see that central ring there?
Mm-hmm.
That's really obvious in this gravity data, right? And you can even see some outer ring structure as well, which is really cool. So this is kind of what we used, or what scientists used, to kind of say, oh, this kind of looks like a crater.
So out of curiosity, you said that the size of the space rock, wherever it hits, that dictates what type of crater you're going to get. So does size correlate to energy? Because you also mentioned that the energy pops up and makes these ripples. So is that correlating effects then?
Definitely, yeah. The larger the collision, the more dramatic the collision, the more energy is imparted into the planet. And this can have really, really devastating results that we're going to be talking about here. The smaller craters, you know, that sort of thing might only have like locally devastating events, you know, but these types of Chicxulub scale impact events were horrible for the entire planet. I mean, I want to talk just a little bit about some of the devastating effects of the Chicxulub impact, because it really can give you a scale of how much energy was actually imparted by this impactor. So everything kind of in that 31 mile across kind of region, that would have been pretty much instantly vaporized, really dramatically awful. But in a really, really unfortunate situation, the place in the Yucatan Peninsula that the Chicxulub impactor would have struck, right near Chicxulub, present-day Chicxulub, at the time, that was all underwater. So that was a shallow sea. And this may seem like, okay, well, why does it matter? It's still a giant space rock. Because a giant space rock striking a shallow sea would have caused a global tsunami. So a 100-meter tall wave would have traveled across the entire planet, causing flooding, killing marine and coastal life all over the planet within a matter of hours. What's more, it would have shot like water vapor up into the atmosphere that would have then mixed with salts from the region that it impacted, causing acid rain all over the planet, which would have sucked pretty much.
Yeah.
Yeah. It also would have caused like molten gas and molten rock, or vaporized gas and molten rock, to be shot up into the atmosphere, which then would have rained down, causing global wildfires. There would have been earthquakes. There would have been volcanoes. There would have been like insane smog that would have blanketed the entire Earth and blocked out the sun. All of this is to say that pretty much 75% of all plant and animal life on Earth was extinguished by this event, which is just truly like impossible to imagine in my mind. Like, I don't know if you guys can imagine that, but I certainly can't.
No, that's crazy. So so it takes generations for this to, I guess, work its way through the atmospheric system. Is that accurate? Or
yeah, that is accurate. I mean, there were certain effects that would have caused instantaneous, death, like the vaporizing of things close to the impact site, but this would have lingered in the atmosphere for years, and it would have just continuously pummeled all life on Earth until it was all dead.
Wow.
So
needless to say, there was some climate change going on definitely back then too.
yes, there was very dramatic impact caused climate change. And you can see just how dramatic this would have been on the climate, yes, but also on our geologic record in general. That image that I've got there on the right, this is a picture of basically the impact, right? So on the bottom part of this image, this is a chunk of rock from near the impact site. And if you look at this image, on the bottom is rocks from the Cretaceous period, and then on the top is rocks from the Paleogene period. So these are periods in Earth's history. That middle band, that brown stripe, that is all ejecta material from the impact. So that's soot, ash, dust, debris that was kicked up by this impact and spread across the planet.
Wow.
So so dramatic that it caused this horrible event to be recorded forever in our geologic history.
I don't want to repeat that.
No, me neither. Thankfully, we won't have to, probably, maybe. Cross your fingers. But, you know, as large as this Chicxulub impact was, it was not unheard of in Earth's history, right? We had a couple of other that were of this scale. We see Vredefort, which is a impact crater in Free State, South Africa. And it's a little bit bigger than Chicxulub. It's about 10 kilometers larger than Chicxulub, so on the same scale. We also see Sudbury, which is an impact crater in Ontario, Canada. It's about 20 kilometers smaller than Chicxulub, so also on the same scale. But what you'll notice about these two is that they're both much, much older than Chicxulub. So Vredefort is 2 billion years old. Sudbury is 1.8 billion years old. And we said that Chicxulub was only 66 million years old. So the difference is Chicxulub would have happened, would have existed when life was thriving on our planet. These other large impacts probably would not have, or would have impacted when life was still just getting started. So that is also what made the Chicxulub so devastating, was that it was so recent in our geologic past.
So would these be technically considered other extinctions? And I'm trying to think of the Field Museum. I went through their new Sioux exhibition right before COVID hit.
Oh, cool.
I really didn't understand what I was looking at, but I was very fascinated by it. And they were saying there was different extinctions. Does this correlate to that, or is that something completely different?
Oh, I'm probably not the right person to ask this. I know there were different extinction events. I don't know if they were all impact induced. I know that that's been theorized for sure, but I don't know where the consensus has landed.
So go back to the museum then.
Yeah, for sure.
Yes.
I will be Googling because, yeah, that would be, I don't know. But I imagine if there was life on the planet when these impacts happened, it would have been devastating. So thankfully, though, not every impact event is as large and devastating as Chicxulub. This next one that we're going to be talking about, I like to talk about because it is our own impact crater here in Indiana. And I think it deserves to be highlighted, and it has a really cool history. So I like talking about Kentland when I get the chance. This is Kentland Impact Crater. This is an impact crater that's about 12.5 kilometers across. And it is older than Chicxulub. It's about 97 million years old. So not quite the 2 billion years old of Vredefort, but still pretty old. And this is a complex crater. So it's not a peak ring crater like Chicxulub with that central spread out ripple. This just has a nice central upflip. But what's so interesting about this crater is that there actually is no perceivable crater from the surface, right? You don't see a basin, you don't see a rim, you don't see a central peak, nothing. It's just flat. And if you know anything about northern Indiana, you know that it's all flat up here. Everything's flat in northern Indiana. And that is basically because during the last glacial maxima, as the glaciers were retreating from here in Indiana and moving back up northward, they scraped away any sort of topography that would have existed on the surface. So things like mountains, hills, crater rims, all would have just been ground down to a pulp. So that leaves us with this flat area that used to have a crater, doesn't have a crater anymore. And it wasn't until like the 1800s that farmers on the land started noticing that they had sort of like weird limestone deposits in their farmland. And this was really good for them because they got to then turn that into a limestone quarry and make a bunch of money. But people were starting to think, you know, why is there this weird uplift of limestone in this field in Indiana? That doesn't make a whole lot of sense. How did this limestone get so close to the surface? Now, geology, there are a lot of ways that limestone can get so close to the surface that any sort of uplift can happen. Can be, you know, weird erosion, weird volcanism, weird tectonics. There's a lot of weird stuff that can cause an uplift in geology. One weird thing is impact craters. So we talked about that central peak, right? We talked about how that's a rising up of material from underneath rising into that central peak. And that was one of the theories for a long time at Kentland was the site of an impact event, but we really had no way of proving it. You know, in science, we don't like to say prove, but we do look for evidence that is more or less definitive. And we didn't have that here. So for a while, it was just floated around. as a theory or a hypothesis. So during these quarrying activities, they had turned the Kentland region into a limestone quarry. It is still a limestone quarry today. During these activities, workers started to notice that they were finding these like weird fractured rocks in the region that they were quarrying. So you can see some of these rocks, or an example of what these rocks might have looked like here on the slide. And what these are called shatter cones. And it wasn't until like the 1970s that we finally figured out for sure how we think these things formed. And there are only two ways that you can form these known to science, right? First is an underground nuclear explosion. We don't think those were happening in the 1800s in Indiana. Maybe, probably not. The other is an impact event. So if you find these in a place that you know you weren't doing any sort of nuclear testing, more or less, you can confirm that this is an impact site. So how do these things form? There's still some debate on it, but what we think happens is that shock wave from all of that energy that's being departed, we talked about how there's so much energy, sends a shock wave through the material that it impacts, right? And that shock wave travels through the rock, and when it strikes off of any sort of heterogeneity, any sort of anomaly in the rock, be it like a weird sized grain or something like that, it scatters, that's what I was looking for, scatters the shock wave, and it forms these conical fracture lines away from the point of impact or of striking off of that grain. And so these conical fractures, these shatter cones, form in these types of events. And it leaves behind these iconic things that we can kind of look for and say, yep, for sure, we think this was an impact crater. And by the way, we were talking about, you know, the amount of energy that this causes. If you can compare it to a nuclear explosion, I mean, that can give you a pretty good idea just how much energy you're delivering in these kinds of events. So, wow. Yeah.
Is this site of being actively investigated? Are there ongoing studies of it?
Yeah, so it's still an active quarry. So it's still being quarried today.
Okay.
So it's not a place that you can just kind of show up to. I've been there as a part of like my department did a trip down there or up there. And it is, you know, the people that work there are great. They're super helpful and, you know, but they have a job to do, right? It's their quarry. So they can't just stop operations to let scientists go in there and take whatever measurements they want. So they're super great, super awesome, but, you know, got to respect that they've got a job, so.
All right. There's the bottom line. Yeah.
Exactly. But as we talked about, if you want to go to a impact crater that you can go to, you can see, perfect tourist opportunity. Meteor Crater is super, super awesome. We looked at Chicxulub, which was that peak ring. We looked at Kentland, which was the complex singular peak. Now we're going to look at the smallest type of crater that I look at, which is Meteor Crater, the simple craters. So Meteor Crater is arguably the best preserved impact crater on Earth. Certainly, in my opinion, it is. I think other people might, you know, have other opinions, but I think it's the best. And that's because it is really, really young. It is only 50,000 years old. So compared to the millions we were dealing with, the billions we were dealing with, 50,000 years old is nothing.
Baby crater.
Baby crater, exactly. And baby in size. It's really tiny. It's only like 1 kilometer across, which I think you said is what, 0.6 miles?
Yes.
So really small. And it hasn't been subjected to water erosion like Chicxulub. It hasn't been subjected to glacier erosion like Kentland. It formed in a desert in Arizona and pretty much looks the way that it would have looked 50,000 years ago, more or less.
Wow.
Yeah. So this is a simple bowl-shaped crater. You might look at it and you might think that it looks a little bit like a square almost. Like you can kind of see that it's got like 4 corners or so. That's from faulting after the formation of the crater. It would have formed in a bowl, but then we had some fault lines that kind of messed it up a little bit. But if you want to see a crater in real life, I highly recommend this one. It's a bit of a, it's kind of a tourist trap, but it's like a fun tourist trap. And I highly recommend people go there. You can see like the actual asteroid or meteor that they collected. Super cool.
My family and I were there a few years ago when we were out in Arizona for a trip and really enjoyed it. What's crazy to think about, I thought, gosh, this is really big and wide, but when you're telling us this is just a baby and thinking about one spreading to Owensboro, Kentucky, that's incredible to think about.
Yeah, it's really crazy. I'm so glad you've been there. I think it's super cool. So I'm glad you guys made a stop there.
So I've been to I'm going to butcher this, Ubihi Crater in Death Valley, California.
I've never been to Death Valley.
I miss it. Oh my goodness, it's beautiful. And I guess it's a question too. So what's really neat about the Native American tribe that lives with Death Valley, used to work for the National Park Services out there. That was where they believed life came from. Do you know if there's any association with that thought process with this particular meteor crater?
I don't know about any sort of like local traditions or local thought processes. Probably not, I would say, given the fact that we didn't know. Oh, you're talking about Meteor Crater. I'm sorry. I thought we were still talking about Kentland Crater. I don't know. I don't know about Meteor Crater. I do know that there are a lot of local traditions and things like that involving it. I don't know specifics. Speaking of life coming from craters, though, I do have a thought on that.
Yeah.
So it's thought that the majority of water that exists here on Earth came from impacts with comets. So the idea that all of the water that is brought to our planet came from these impact events, I mean, that is our life, right? We need water to live. So the idea that craters represent life, I think that's really accurate. I mean, I think that's beautiful and true. I mean, that's how it works. So that's
So
really cool. I didn't know that.
Just in way of background, so meteors are made up of ice, and such as that to be bringing us water.
So comets can be, meteors are just kind of a catch-all term for any sort of body that is falling through our atmosphere, ready to strike us. They can be asteroids, which are rocky bodies, or they can be comet remains, which are icy bodies. So you can have comets from the outer solar system carrying ices, water, that sort of thing, or you can have rocky bodies from like the asteroid belt, that sort of thing. So it can really be anything. And meteor is just kind of what we use to classify them all.
So the comets would have been what was bringing us water in the form of ice.
Exactly, yeah.
Wow.
That's
So
interesting.
I don't know about, you said Ubihi Crater?
Yes.
Is that what you, yeah, I don't know what formed that one. I haven't done any research on that. That's really cool. I will definitely be Googling it. And I highly encourage you to Google some of the local thoughts on Meteor Crater as well, because I know that there's a really rich tradition around that as well. So very, very cool stuff.
See, there's some cultural heritage link in there in the art history.
I have a slide on art history. I get into the art.
Well,
I get into the art.
Well,
Towards the end.
that'd be interesting to know, because I know there's several Anasazi sites around the Meteor Crater area that we visited too. Yeah.
And I know that for much of history, it was kind of known that this was an interesting site. You know, the local people had collected bits of iron meteorites, you know, and incorporated that into their tradition.
Wow.
Because, you know, Meteor Crater is really cool in that they have a majority of the impactor, the asteroid that struck. It's in the gift shop, or in the I guess the museum that's attached to the gift shop. So we have that, and we have little bits of the meteorite strung all over the surface. So yeah, very cool.
Wow.
So moving on from Earth, we're going to hop off Earth onto the moon now. So there really is no better place in the solar system to study perfectly preserved craters than the moon. Pretty much everything that happens on Earth, the water that we have, the air we have, the wind, glaciers, everything that could mess up a crater doesn't exist on the moon. The only thing that could mess up a crater on the moon is another crater. If a crater strikes on top of it or covers it up somehow, overlapping it. So this is really great for us because we can learn everything that we've learned about craters on Earth, we can apply to the moon in like a really great test case. So I think the moon is, I don't focus on the moon, I focus more on Mars, but the moon is really great because for the thing, you know, we don't have any samples from Mars, right? As much as I wish we had samples that we brought back from Mars, we don't have that. On the moon though, we do have that. We have sent humans to the moon and brought back craters for, brought back rocks for us to study. So we've dated these samples that we've brought back, and we know just about how old these rocks are. And knowing what we know about crater counting, we can take these rocks from the moon and we can say, okay, this rock is 3.9 billion years old. We collected it from a place that had 10 craters. If we look at this place that we haven't been to and we see that it has 20 craters, we know it must be older than 3.9 billion years old. And if we look at this spot over here that has 5 craters, we know it must be younger than 3.9 billion years old. So this is how we link radiometrically derived ages, lab-derived ages, to places we've never been. And this is really, really important. This allows us to kind of extrapolate what we know about a very specific portion of the moon to the entire moon, which is really, really cool. And we can extrapolate it to places we've never visited. So on Mars, we have this really nice middle ground between heavily eroded Earth and perfectly pristine moon. And on Mars, we know that there was liquid water in its past. We know that there's currently wind. So what we see here is an artist's rendition of an ancient Jezero crater. Now, you may or may not know, Jezero Crater is where the Perseverance rover is currently exploring. This is the rover that NASA landed on Mars in February. So the Perseverance rover is wandering around Jezero Crater, and it is so important that they picked Jezero Crater because we see that Jezero Crater kind of offered a like a cradle for life to exist possibly on Mars in the past. This is one of the best places that we think we could go to look for life on Mars because it infilled with water at one time. It formed a lake. We see inflow channels, we see outflow channels, sediment. We know that this was a lake and we know that life can flourish in lakes. So we think that this is a really great place to look for life, and that's why we've gone there. So we can kind of get a better idea of when liquid water flowed across the surface, how craters interact with water, how they interact with, how they form these places that life could possibly flourish. So I think that that's really cool.
I'm sure a scientist is going to laugh at me for asking this, but if we can fly rovers to Mars and land and they can do their thing, is there any way we can extract material, soil, rocks from Mars and send it back to Earth? Is that in transit or is that just too darn expensive? I don't know.
No, that's exactly what we're planning. That's
the
goal. No, you're right.
Go scientists!
Perseverance, which is currently wandering around Jezero Crater, will cache samples. It will collect samples, cache them, and drop them on the surface. And then a return robot, probably in the 2030s or so, will go back to Mars, pick up the cached samples, and bring them home again. So you are exactly right. That is NASA's goal. We want to get samples from Mars any way we can. Robots, people, any way else.
So are they able to analyze it somewhat there on the Mars surface and send back data to here?
Yeah, for sure. We can get a pretty good idea of the composition of the rock just by picking it up and analyzing it through our rovers on Mars's surface. We can get a good idea of a lot of things actually with our rovers. That's why they're so critical and so important. We can understand so much about the surface without us having to actually go there. But there are some tests that are better performed by people in laboratories. And one of those is age determination, is something that we really need to have here back on Earth. So, and that's what I care about. So,
well, maybe in your guys' lifetime, someone will step foot on that red planet.
Tom, we're sending you.
Well, they better have the Wayback Machine.
Well, according to your background, you're halfway there.
I'm a pessimist. I don't think we're going to set people on the planet Mars anytime soon. I hope I'm wrong.
No, okay.
But I'm in the minority, I think. Most people are like, yeah, we're going to do it. But
is that because of the vast technological challenges that would involve?
Yeah, to support people, I mean, you need air, you need water, you need food, you need ways of disposing waste, and you need so many things that you just don't need for robots. Robots don't need to eat, they don't need to breathe, they don't need to do any of that stuff. So they're really perfectly situated for this planet. And I'm so happy we have rovers so people don't have to go deal with any of this stuff.
Yeah.
Okay, so
Wow.
I wanted to kind of wrap up this portion and get into the last portion, which is kind of what I do and my research. So like we said at the beginning, I use computer modeling to study the evolution of the solar system. Particularly, I focus on the earliest part of the solar system, so solar system formation, and really the formation of the terrestrial planets. So this is Mercury, Venus, Earth, and Mars.
Wow.
And what I kind of do, my goal is to connect a simulated population of early solar system bodies. So this is asteroids, comets, maybe other things that would have been around in the early growing solar system. And I want to connect those to ancient observable craters. So the simulated population, the computer generated population to observable Martian craters is kind of my goal, to make that bridge. And the way that I do that is I kind of like to think of myself as like a little detective. So I come across this crime scene, and in our case, the crime scene is the surface of Mars. And I try to do what any good detective would do, is I try to learn as much about the events that happened at this crime scene as possible. And now I can't go back in time. I can't go back and witness what exactly was taking place. But what I can do is I can gather evidence, and I can use that evidence to come up with hypotheses that are then supported by this evidence. And this is really how the scientific process works. And this is why how we can learn so much about a planet that, you know, we weren't around to witness. So the types of evidence that I would look for as I'm studying this surface, we've already discussed the number of craters can be a really good indication about the age of the surface. But I also can look at the size of the craters. We know that bigger craters formed from bigger impactors, and this can give me kind of a really good idea of the types of bodies that were existing in the early solar system. The size of the asteroids, how many asteroids there were. Were they asteroids at all? Were they something else? I also look at the spatial relationships between these craters. So as we can see here, we have 3 craters all overlapping each other on Mars. We know from how craters form, the one on the bottom must be older than the middle one, which again must be older than the topmost one. And so these kind of spatial relationships can really give me a better idea of the ages of different surface units and the sequence that events took place on Mars.
So the size of craters on Mars, how might they compare to like the 31-mile across one? I'm assuming they vary in size.
Yeah. So they do all vary in size. Let me go back to a picture of Mars here. They do all vary in size, but because we know that impact events are kind of random processes throughout the solar system, they're going to strike Mars just as often as they're going to strike Earth, just as often as they're going to strike the moon. The difference is on Earth, we have oceans, we have plate tectonics, we have things that are erasing these craters after they've formed. Where on Mars, we have less of that, and on the moon, we have even less of that. So on Mars, we do have craters that are altered by, you know, large lakes, ponds, rivers, that sort of thing. But we also have these relatively, I mean, you can see these craters are more or less, you can see that it's a crater, right? It's not covered by an ocean or something like that, like we have here on Earth. So the sizes that, we think the sizes of craters that would have struck Mars are the same as Earth. We kind of just have to assume that because we know that it's a random process. So if you're comparing to like a Chicxulub scale, like the Evansville to Owensboro type crater, we do have a ton of those on Mars. We have a ton of them on the moon. Just like we probably have a ton of them on Earth, we've just completely eroded them. We don't see them anymore. So the last part of this I want to talk about. Now that we've collected all of our evidence from our crime scene, it's kind of time to put together everything into a profile of the suspects that we're considering in our little ancient cosmic collision case. So in the past, researchers have considered things like asteroids, comets, these types of things as the impactors that could have formed the most ancient craters on Mars's surface. Unfortunately, or fortunately for us, new research has shown that the timing of these impactors, these asteroids and comets, might not actually be right to account for the most early craters in Mars's history. So my research is taking kind of a different approach. I'm looking for other sources of impactors, other types of bodies that would have existed. In my work, I study something called collisional fragmentation. So in other words, I consider the debris that forms when two large bodies collide with each other in space. We know that collisions between planets is how planets grow. They collide with other bodies and merge together to form an even bigger body. But we also know that this process wasn't perfect. So, I mean, you know this logically, right? If you come across, a car crash, the two cars didn't collide perfectly and merge into one bigger car. That's not how that works. You see debris scattered all over the place, right? And the same thing happens in the solar system. When two bodies crash, there's debris everywhere. And that's what this video shows here. I think it already played. But you can see there, two bodies colliding with each other. I'm gonna play it again. Two bodies colliding with each other, all of this debris being generated, and then some of that debris colliding with another, bit of debris and forming even more debris. And this is really important because this is a population of bodies that haven't previously been considered in models of solar system formation. For the most part, people have been assuming that two bodies collide and perfectly merge, and there's no debris. It's a clean, easy process. But I think my research is finding that that's not quite the case. Eventually, if these fragments stick around long enough, they could end up on collision courses with fully formed planets like Mars. And when these fragments collide with Mars, they would form impact craters. So basically, my research, I aim to link debris populations from this early solar system formation events to populations of observable Martian impact craters. And I hope to gather enough evidence to show that fragments could be responsible for most of the ancient craters on Mars's surface.
Wow.
So
out of curiosity, when you have these two bodies that collide, I was always under the impression with my 2 classes of astronomy, which is nothing, but that when they would collide, I guess the heat and the pressure and the orbital rotation would pull this together and slowly start to form planets.
Exactly.
Oh.
Yeah, no, you're right. That's how we think planets form for the most part. It's a process known as accretion. Is two bodies, you're exactly right, collide. There's a lot of heat. There's a lot of energy going on. Gravity is pulling them together, and they are more or less growing into bigger bodies. But that process isn't perfect. So debris is shot outside of the gravitational region that doesn't get fully accumulated back into the growing body.
And that's what made these craters on Mars, is what you're tracking.
That's what I'm hoping. That's what my research is kind of trying to show. Yeah, so I'm trying to show that this debris that would formed from these collisions that weren't perfect collisions by any means would have then existed in the solar system around the time that Mars was accumulating these craters. So could be a population of bodies that isn't previously considered.
Okay, so I guess, and sorry, this is a stupid question, because I feel like it's going to be.
There are no stupid questions.
So basically, you're just trying to find, your research focuses on the origins of these craters.
Exactly.
Wow. Can I follow you around?
Yeah. You're exactly right. Yes, I am trying to study what formed these craters. We see all of these craters. We see this crime scene of things that we don't understand. And I'm trying to figure out, kind of like Nancy Drew, like, who done it, Like, what made these?
Yes.
So all of this sort of fits together. Your research and other scientists do fit together sort of in the puzzle of the formation of where we're at now and the creation of the planetary system, et cetera.
Yeah, exactly.
Wow.
I'm, trying to, each of us just plays a tiny little part in trying to understand how our solar system formed and all of the different parts of it. And I think that's what's so great about science, right? Is that we all work together and we all kind of have tiny little pieces of the puzzle, trying to put together this idea of where we came from and what our planet used to look like. So
Yeah, that's fascinating.
Is it strange to not be able to work with something tangible? Like, everything you're doing is like literally not, like, I can't pick it up. I can't.
Yeah.
You can't go there in the case of Mars.
Right.
Or the moon. Yeah.
Whereas Tom and I can just go downstairs and, we have our collections. Like, is that hard?
Right.
It's certainly something I had to get used to. Actually, in my undergrad, I was studying galaxies. So I was in astrophysics as an undergrad.
Wow.
And I did find that galaxies for me were just, I didn't like that I couldn't imagine, it was hard for me to put my head in that space, which is why I switched to planetary science, which I do find to be more tangible, at least for me. And, for me, I do a lot of computer modeling, a lot of simulations, but I have planetary science friends who do tangible things. They study meteorites. They go to analog sites here on Earth that could be Mars, analogs to Mars sites.
Wow.
So it is a tangible field. My work is probably less tangible than some, but.
So these we do track things that are going through the sky that could impact the Earth or other places. So we know when they're headed around here and
yes.
name them and classify them. Is that true?
Yeah, you don't have to be afraid of being randomly struck by a meteor, because NASA's on pretty good. We pretty much know what's coming about in our area of the solar system. But that wasn't always the case. And that brings me to my last slide, actually, which is the art and history intersection here. So because this is an art and history museum, I wanted to include just a little bit of art and history. Like we were saying, people until the past 50, 60 years or so were really kind of just existing at any point. They could have been struck by a meteor and they would have had no idea. So this here is a woodcut depicting the fall of the Ensisheim meteorite in 1492. So this is a meteorite that fell in what is present-day France in 1492. And this woodcut here is from the Nuremberg Chronicle, which recorded the event a year later. And as you can see here, people in this time were so awestruck by this event that they wanted to engrave it into their town history forever. They depict here this meteorite being kind of spit out from the clouds and landing in a field. This was a really small impact event. The crater that it formed probably wasn't more than a couple of feet across. Nobody was injured or anything like that. But these kinds of things are so impactful,
Yes.
impactful
Yes.
to human history. I mean, it's something that will stand out with you. And if you were lucky enough to witness something like this, I can't imagine you would ever forget it. Humans have existed alongside impact events forever, and we will continue to exist alongside impact events.
I can imagine somebody back in 1492, may God strike me dead if I then boom. So.
Exactly. Yeah. And I mean, we were talking about, some of the local people in Death Valley and these things. I mean, every culture had discussions about meteors. Meteors struck the Earth, and every culture had a way of thinking about that. And it's really amazing that we have such a rich human history surrounding impacts and impact events. So
is there any, this is a silly question, but is there any record of anybody, being hit by a meteor? I know the chance of that would be infinitesimal. But
yes, there is one person in all of human history that we know of that was hit by a meteor. I believe it was a woman in Alabama, like in the 50s, I think. Correct me on this. It's Googleable. You can Google it.
Okay.
It fell through her roof, and she was sitting on the couch, and it hit her knee while she was sitting on the couch. So yeah, that's like the only time.
So it's not a fatal blow. That's good.
No, she survived.
That's
I'm
crazy.
pretty
Well,
sure it was a woman.
my gosh. How many billions of people have been alive? I'm one in whatever billion that ever been hit by a meteor.
Yeah, exactly. So, we don't have too much to fear here. It's not like we're all going to be wiped out in the next extinction event anytime soon. So,
and it's funny you say that, because I remember, at least in the last 10 years, there's two huge hypes that this meteor is going to come and wipe out humanity. And I'm like, oy vey, I mean.
Honestly, with the year we had, I wouldn't put it past us anymore. But yeah.
So Carlisle, may I ask, when you are finished with your PhD and you are doing whatever, what is it that you
I'm curious
want
that
to
too.
continue focusing on, what you're focusing on, and what are your career where do you see your career going? I realize that changes for us as we go along, but right now, where would you see it going?
No, I should probably have a better answer than I do, considering I'm, 4 years into this and not too much longer to go. I love my research. My enthusiasm for this, it's so cool. I think this is like the most awesome thing ever. And I would love to be able to continue doing this research.
Yeah.
But I also had a wonderful experience at the Evansville Museum. I really, really enjoyed the teaching aspect of things. I enjoyed working in a planetarium. I would certainly like to be able to do that again in the future as well. So who knows? I know that there are a lot of planetariums. Universities and colleges have planetariums. I think that would be a really great place for me to be able to kind of merge research and planetarium work, but we'll see. I still got another 2 years to figure it out. So
Oh, that's exciting. Yeah.
But yeah, so that's kind of where my presentation wraps up. I just want to say, impact events are a vital part of life, and they can teach us so much about our solar system, about our place in the solar system, our place here on Earth, and our history as people. So I think they're really cool, and I really encourage people to, Google impact craters, read as much as you can about them because they really are so great. So yeah, thanks for having me, guys. Want to wrap things up here and we can answer any questions or have a discussion. I'm down for that.
Well, yeah, thank you so much. It's really nice of you to share this time with us and to share it with our the visitors that will be seeing this via the internet.
Well, thank you. This was really wonderful, and I hope if anybody, if somebody watches this and they have a question, I included my email, I believe, at the beginning of this slide. So feel free to shoot me an email, and hopefully I'll be able to answer your questions.
Well, again, to echo Tom, thank you so much. This is so fascinating. I'm always like, ooh, I want to learn so much more about science.
I feel the same about art and history.
Yay!
Yeah. Well, that's what's so great about our museum is there's Tory and myself, but we have a wonderful science department with Mitch Lumen leading us down that road, and a fabulous Cook Immersive Theater that provides all kinds of opportunities. So we're fortunate here in our neck of the tri-state of our region to be able to focus on all those disciplines along with our great educational programming.
And if you ever have a moment, if I can give one more housekeeping, if you ever have the opportunity to watch our science demonstrators conduct experiments in our science area, do it. I spent 2.5 hours there without even realizing it.
What was the demonstration?
It was making goo, making all sorts of stuff, making things explode. But my mom visited. This was 2019, and we sat for 2.5 hours there just doing random experiments for 2.5 hours. She never saw what I did. We just had so much fun in the science section, and really, I can't echo Tom enough. We're so blessed to have what we have in Evansville, to have the art, history, and science united underneath one roof with fantastic education. So I'll just parrot Tom, but really I can't express how grateful I am to have these opportunities and to share them with our public.
Definitely.
We invite everybody to come down to the Evansville Museum, and Tory, correct me if I get our hours incorrectly. Thursday, Friday, and Saturday, we are open from 11 to 5. Sundays from 12 to 5. So those days you can come in to our physical setting and see what the great things that Tory described earlier. And you can always check our website, and also our Facebook page has a lot of up-to-date information that will cue you in on what is happening here at the Evansville Museum of Arts, History, and Science. And appreciate your being with us on Tipsy Topics today. Have a great
anniversary.
1 year anniversary. Yeah, Tory and I, we teamed up on this, and it's been loads of fun. And we're keeping going. We have upcoming plans for episodes throughout the rest of 2022.
That's really exciting, guys.
Well, thank you. We wish everybody a fond farewell.